Hey you cats and kittens? That doesn't sound right. I'm Matthews. We're checking out 8-6 binomial distribution and probability. Oh, don't worry about that. So, we're just spinning a spinner. We're taking this spinner, in fact, evenly distributed, and there's 3 blue sides and 1 white side. And if you spin it once, and you don't blow on it or anything, and you have everything's even, you have a chance of this landing white side down or one of the blue sides down. And if you were talking about your instance of a success being landing on the white side, maybe you don't know homework, right? If you land on the white side, something like that. 1 is a success and 0 is a failure because you hopefully don't want homework. I don't know. So 1 out of those 4 times will, I want purple. I feel like purple today. 1 out of those 4 times you'll get the spin that you want, and therefore 3 out of those 4 times you'll get not what you want, right? Fine. So that's this. Either 1/4 of the time it lands on the white like you want, and 3/4 of the time it lands on, I think this was supposed to be a B, not an E, blue. If you did this twice, you got 2 spins. A couple of things that could happen. You could have an output of, you'd still have 1/4 and 3/4 for your first spin. As long as you don't damage this, it doesn't matter what, the probabilities don't feel each other's presence. So your second spin has the same 1/4, 3/4, right? Regardless if you got a white on the first time or a blue on the first time, it doesn't really matter. You have the same probability. So for you to get we're calling X being landing on a white. So for you to get 2 of them, you would have had to have followed this path, white and a white. That means, therefore, that white, to get 2, you would have had to landed on white twice, right? And you'd multiply these together. You'd say 1/4 times 1/4, which is 1/16, right? I'm going to call it 1/4 squared, though, just because. For you to get no whites, you would have had to land on, or you would have had to have followed this branch, 3/4 and 3/4, right? And maybe I'll do those in blue. Let's call those 3/4 and 3/4. You would have had to have, and I'm going to off-center it, 3/4 and 3/4. And you would have had to get 2 of those. Meaning, well, I choose purple as a badge. Meaning that you got 1/4 no times, and you got 3/4 twice. 1/4 of the 0 is 1, so it doesn't cancel this out. Oh, and also, here with this line, you would have had to have gotten the 3/4 probability of getting a blue no times. Now, also, you could have gotten a white once, either by doing this. Let me get some deletion going on. Either by doing this branch where you get a white first and then not a white, or by doing this branch where you get not a white and then a white. Either way, you get a 4th and a 3/4 in whichever order. So if you thought about this part, you really got 1/4 once, and you got 3/4 once. But there's a little hiccup in there because you got all of them. You got that happening. There's 2 ways to do that. So here there's only 1 way to do this. Here there's only 1 way to do this. So I'm going to put some 1s in front. But here there's 2 branches. 2 branches where you get a 4th and a 3/4 and 3/4 and 1/4, and whatever this probability and this probability are, I guess it's 3/16 for each of them. You'd add that up 3/16 of the time this happens, and also 3/16 of the time this happens. That's why you have 2 sets of there, so 6/16 of the time. But there's only 1 branch for this and 1 branch for this. Do you smell what I'm smelling? Sense? That kind of sounds weird. Let's do this with 3. Right, same spinner, we spin it 3 times. Oh, don't look. If we played the same game, you'd only get a white 3 times in a row. We're saying x is the whites. You'd only get a 3 in a row if you followed this branch, and you got a fourth and a fourth and a fourth. Right? So therefore, you would have gotten the 1/4 3 times, and you would have gotten a blue, which occurs 3/4 of the time. 3/4 of the time. None. And there's only one way to do that. It's only that branch to get 3 of the whites. Similarly, you could have gotten 3 blues in a row, which means 0 whites, by having 3/4 and 3/4 and 3/4. Now, that means you would have gotten 3/4 3 times. Also, you would have gotten 1/4 no times. To the 0 power makes it a 1. Anything to the 0 power is 1, so we're not like canceling this whole thing out. And there's only one way to do that. Right? There's a couple of ways to get 2 whites. Here's one way: white, blue, white. And here's another way to do it: blue, white, white. 2 whites. I don't actually care, right? Like, so you get 2 whites at any point in the 3 spins. You don't have to exactly 2 whites. You don't have to do any homework, right? So we would want the white, which is 1/4 of the time, to happen twice. If we say we have to get exactly 2 whites, well then therefore you need the 3/4 probability occurrence, which is the blue, to happen only once. Oh, and also there's 1, 2 branches that make that happen. Are there 2 branches? Maybe there's another branch. 3 branches. Good. There's 3 branches. Why didn't you say anything? Right, there's another branch. White, white, blue, 2 whites. White, blue, white, 2 whites. Blue, white, white. So there's 3 ways to do that, which is good. And finally, if you said, I want you to spin twice, you got to hit white once and only once. There's a couple of ways to do that. White, blue, blue. Blue, white, blue. And blue, blue, white. Either way, blue shows up twice. So the probability of the 3/4 shows up 2 times. The probability of, why did I choose purple? 1/4, the white, only shows up 1 time, 1 time, 1 time. The Fujis? Look up the Fujis. 1 time. And there are 3 ways to do that. Do you see what's happening? Do you see it? You're like, yes, I've seen it. I saw it coming. You wrote it at the top of your notes, Gorkevich. Just say it. It's the binomial probability that's coming back. It's the binomial expansion. Yep, so it's binomial theorem again. And so we're going to work with the probability that you want to a certain power, the probability that you don't want, the converse, to a similar power, 1 minus that, and an n choose r factor in front. Here's the fine print. Yeah, failures are called 1 minus the probability that you want. It's the converse. This is the binomial probability distribution function, the BPDF. For those of you that like to truncate things, this is, you pronounce this as which is exactly the sound that you make when you punched in the stomach, and also when you realize that you have to do the binomial distribution again, and not this again. It's not too bad, sort of. Let me show you. Okay, let's play this game one more time with left-handed and right-handed. So 10% of the population is left-handed. That's kind of, the statistics is fairly accurate, actually. So I want to take this and think about what's the probability that if I have 3 offspring, I'm not going to have 3 offspring, 2 is fine, take your time, don't rush into it. But if one had 3 offspring, what's the probability that exactly 2 would be lefties if 10% of the population is lefty? Okay, so here's what could happen. This is offspring number 1. Hello, offspring number 1. This is offspring number 2. The middle child's always weird and like angsty, and this is the 3rd child, which is always the best and the most admired by the family. So here's what could happen to your parents, or the parents. You could get 3 lefties. Right? The probability of that happening is 0.1, 0.1, 0.1. You'd multiply along that branch. It's a small probability, right? Very small. It's, well, 0.0001. You could have a lefty, lefty, and a righty, right? Lefty, lefty, righty. And this is the probability if you multiplied along this branch, 2 lefties, and then your third best child is a righty, etc. And you keep going. This is a left, right, left. This is a right, left. You get the idea. There's all the ways. This is all the things that can happen. And interestingly, well, vitally, is that if you found this probability, this one that you calculated for you, this one, this one, this one, this one, this one, and you add it all up, what do you have to get? Yes, 1. You have to get 1 because 100% of the time something's got to happen. You're not going to get a squid, hopefully. Okay, so these are calculated for us because they asked us specifically about exactly 2 lefties. And here's 2 lefties in this, a left, and a right. Here's a left, a right, and a left. And here's a right, a left, and a left. So those are my 3 lefties, right? Left. So we know this probability will give us this branch, that branch, that branch. Curiously, they're all the same value, and so what we can do is just say, I don't know, you win the lottery if you have 2 left-handed children out of 3. Well, this percent of the time you're happy, this percent of the time you're happy, and this percent of the time you're happy. So add up all the different times that you are winning the game, and you get 0.27. Right? This, or 0.009 times 3, 0.009 times 3 is 0.027. So about 3% of the time. Okay, we can do that. We can write out all the probabilities. We could also do this like this. If you didn't want to write all of the probabilities, you could shortcut it. You say, I got 3 kids. I'm planning on 3 kids. Again, take your time. Take a lot of time. Which means that if I want exactly 2, it means I want the green probability, 0.1, I want that to occur 2 times, and I want the other probability, the complementary probability, to happen 1 time, because I'm only having 3 kids, no more, or less. So I want the green to happen twice, here, like that, 2 times there, oh, here, 2 times there, or like that, oh, 2 times there. And I want the right-handers to only happen once. All right, so that's that. But there are 1, 2, 3, there are 3 ways to do that. And so this, you can crunch in your calculator, and you go 3 times 0.1 to the 2 times 0.9 to the 1, and you get 0.027. Did I say 8? 0.027. Neat. So that's the 0.027. That's the long, slow way, but this makes sense to me. If we did the same thing and you said, what's the probability that you'll get exactly 1 lefty? You'd say the same thing, and the only things you would change are the lines that you're looking at, the bars you're looking at. So essentially, we want 1 lefty, we want this one, and this one. And this would be a 1, this would be a 2, and there's still 3 ways to do it. If they said we want exactly, if we want no lefties, well, I guess that's easier. You just say a right, a right, a right. It's just this one. But it's the same thing. We don't have to rewrite anything. We just say I want the 0.01 to happen no times, the 0.9 to happen 3 times, and there's only one branch to do that in. Right? Okay. Let's figure out how to do that with some tech. Right? There's a smoother way to do this, and in your calculator, you go second vars, right? Which is distor. The distor stands for distribution, like probability or binomial distribution. So click second distor, and it pops to this. We'll work with those normal stuff later, next time. Next time. Stop saying that, Gorkevich. And right now, I want to click on Binomial PDF. Binomial, probability, density, a function. Okay. So from here, let's play the same game, right? It's the same prompt. Probability of a left-handed person, 0.1. You want 3 offspring, at least 2 are lefties. In your calculator, this is what we're going to write. Trials. Every child is an experiment. I have 3 experiments going on. The probability of a success. Success is left hand in this case, right? Even if we say it is the probability of what we're interested in. Lefties, 0.1 of the time happen. The x value means how many times do you want that to occur? 2. I want 2 times. I almost said it. Boom, boom. If you have an older calculator, like mine, actually I have an older one even than that, it might prompt you with something just like this, and you have to know where to put what. But most of your calculators will give you that screen that I just showed you, hit enter again, then you get 0.027. Surprised? No. Cool. This is binomial PDF, probability density function. Neat. Okay, so try it. You're rolling a die 3 times. 1, 2, 3. What's the probability that you get exactly? Don't look. Get out of here. Stop looking. Don't look. Close your eyes. Exactly 2 6s. Yeah? Pause me. No, for real, pause me. And try to figure out with this idea. Maybe you want to do it like this. Maybe you want to do it like maybe you want to draw a big tree. Maybe you want to do it like this. Maybe you want to, well, maybe first try it like this. I think it would be helpful to see that the values link up. And then try it with your calculator. Neat, neat. Okay, so let's say success is a 6. So success is a 6. I know 1/6 of the time I'm going to get a 6. Right? So 1/6 of the time I will be successful. I'm rolling 3 times. So if I'm rolling 3 times and I want exactly 2 6s, you'd say I want 1/6 to occur 2 times. I want the other probabilities to occur 1 time. I'm rolling 3 times, so this and this have to sum to this 3, right? And there's a modifier in front, right? 3, choose 2. And you could throw that into your calculator in math and prob, right? And choose R. And you could say 3, choose 2, and you'd get 3. Or you could look at your Pascal's triangle, and this is 1/6, so this is 1/6 squared is 1/36 times 5/6, and you can multiply that together. Let's try it. So 3 times 3 over 36 over 6. I'm getting 0.694. Ooh, 0.0694. Another way you could do that is throw it in your calculator and say, well, let's try it on here so you see so second distor, down. We're not going to do all of those things. We want binomial PDF, enter, trials. I got 3, probability is, in this case, 1/6, which is 0.1666. I'm going to put a 7, and I want two values. I want that to happen 2 times. Boom, boom, boom. Hey, same number that I came up with my brain. As the numbers get uglier, use your calculator more, but also I want it to make sense to you. Okay, take that idea, try B. Pause me until you got it. Okay, so the probability of at least 2 6s means the probability of no 6s, I'm rolling 3 times, no 6s, 1 6, and 2 6s. No, at least 2 6s, the other way around. The probability of 2 6s or 3 6s, right? If I say, here, roll this die, if you get 2 6s or more, at least 2 6s, no homework for the rest of your life. 2 6s is good for you, 3 6s is good for you. So, this is the probability of the x value being greater than 2. One way you could do that is say, oh, this works for me. This percentage of the time is when I get exactly 2 6s, and then I'm going to add that to the probability of getting 3 6s, which is lower, but not negligible. So this would be, I'm rolling 3 times. I want 3 of these. 1/6. I want the 1/6 probability to happen all of the times, and the 5/6 probability to happen none of the times. This probability is, well, 3 choose 3 is 1. Tiny squeaky voice out there. Come on. So this is 1/6 cubed. Get out of there. And so this is 0.0046, and this is 1. So this whole thing will be the same, 0.0046, and we'd add it to this one. So plus 0.06. And I'd add those up and get 0.074. Okay. And so this is 2 successes, this is 3 successes, but it's at least 2. So this is what I'm looking for. So the way we do that is say, one of the ways is add 2 and 3 together. Another way to do that is add 0 successes, 1, 2, and 3 successes, and ignore, we could find these two and subtract from 1 if you wanted, right? So you could say, you could figure out what these two were if it was easier, and then all of these probabilities added up should add to 1, because you're either going to get no 6s, 1 6, 2 6, or 3 6. So if you find these two in the same way, you can subtract from 1, and you get these two, which is what we just calculated here. Okay. This brings up the need for being able to find multiple PDFs and add them together. And your calculator can do that for you with binomial CDF. And the CDF stands for cumulative, right? Because it's accumulating. So same idea. What's the probability of a left-handed person being born? 0.1. You have 3 offspring. I want at least 2 to be lefties. So 2 is cool, 3 is cool. So the probability of that x is greater than or equal to 2 is probability of 2 plus probability of 3. With your calculator, you could say binomial PDF 3.12, and you get this 0.27. The probability of 3 would be 3.13, and then you'd add them together. This is good for you. That's a probability of 2 lefties. Here's probability of 3 lefties, and so add them together, and that's a probability of 2 or 3 lefties. You can add them up by hand by using binomial PDF twice and add them your dang self. Or you can use binomial CDF, which is one farther down on the list. C is for cumulative. And so the C, cumulative, you do the same things, but you go trials, probability, successes. So let's try that out. We'd put in, where's my calculator? You put in, let's see, you go second, bars, down. I'll show you what the other parts are for. Binomial CDF, same thing, 3 trials. Probability of a success is 0.1, and the value is, the number I want is at least 2. Ready, go. 0.99, what's up with that? What's up with that is that the calculator is not doing what you think it's doing. The calculator adds up from 0 trials, 1 trial, and 2 trials. So what your calculator is doing for CDF is the number you put in at the end, this number, the 2, is where it stops adding. So it starts at 0 and adds up to 2. So it added these all together. So no wonder it's really close to 1, right? Because this is a low probability. So fine print is that Binomial CDF calculates from 0 successes up to the value that you put in, like in this case 2. So it calculated a PDF of 0, PDF of 1, PDF of 2, and then it stopped adding. So what we got to do is say, let's find binomial CDF of put 1 in, because then, let me steal this because I think it's a good reference. If we put binomial CDF of 1 in, it starts at 0 and adds up to 1 and then stops. So when you put CDF of 3.01 and 1, it adds up these two, and that's 97%. 72, right? So therefore, from above 1 is the rest. And if you go 1 minus 0.972, if you don't believe me, so 1 minus 0.972, voila, you get the 0.028 that we were thinking about. Cool? So we subtract to find the complement. Neat, huh? Okay, so let's do this the same thing again, but let's have 4 offspring. Don't have 4 offspring for the let's do this with 4 and at least 2. If we were to add this up by hand, you could find probability with PDF of 4. This is the probability, and I want 2. This is the probability of exactly 2 lefties. This is exactly 3 lefties. This is exactly 4 lefties. You'd add them up, you'd get that, right? I don't want to add them up by hand. I want my calculator to do it for me, man. So if we just put in binomial CDF is cumulative, meaning it's adding PDFs for you. If we say 4 and 2, it has added, I guess we'd have one more, which would be PX is 4. If you put in 2, it would add all of these together. And that's not what we want with at least 2. We want these. So to do CDF, you would put in 1, and it would tell you these 2 added up, and you'd subtract to get this leftovers. Ooh, somebody's freaking out there. So we find that binomial CDF is 4.1 and 1. It gives us 94.7% is 0 and 1. And so you subtract, and you get that 0.0523 that we thought, which was this and this and this all added up by hand. So here's a little summary. Binomial PDF I think of as precisely. The P means probability density function. But I think P precisely. I didn't want exactly this many successes. And CDF really does mean cumulative. And so there's a little synopsis. They're all in here in PDF, in vars, in Gister. So let's try a couple of problems before your eyes fall out.